Now, in the last example, we saw the normal likelihood, normal model, and normal prior. And we sort of easily found the posterior. The only thing that we needed to do is to complete these squares in the exponent and separate this joint distribution to the product of the posterior and marginal. Now, this is a member of conjugate families because what happened there, we had the normal model, normal prior, but also normal posterior. Now, what is the conjugate family? If the pair F and pi prior form such a combination so that the posterior belongs to the same family as the prior, then we say that pair F and pi is conjugate. So simply you have the model F, you have the prior, and you produce posterior. If the posterior remains in the same family as the prior, then the pair F pi is conjugate pair. Now, if the pair is conjugate, there is no need to find the normalizing constant m of x, which gives you full posterior. In fact, this normalizing constant is the marginal distribution, and you know that marginal distribution is integrating the joint distribution with respect to the parameter, and that integration could be unfeasible. That integration is actually the troublemaker in the Bayesian statistics. However, if you can make the product likelihood times prior and conclude from the product the form of the posterior, then you can, without inventing the normalizing constant by integration, use the normalizing constant characteristic for that family. We had the example with normal. Normal, there is another example, binomial likelihood and beta prior. That was used, if you recall, for the 10 flips of a coin. So imagine the experiment in which we don't know probability of event, of success, but we got X successes, and we model these X successes as binomial with parameters NP. N is the number of experiments, and P is the probability of event, probability of success in each of these N experiments. Now, the likelihood here is a function of P. X is given. Once you observe X out of N, both N and X are fixed numbers. Now, if you put prior on probability pi to P to be beta, the distribution, the density of beta is something similar to the likelihood. There is normalizing constant, which is beta function. This B alpha beta is integral between 0 and 1, P to the alpha minus 1, 1 minus P to the beta minus 1 dP. This is fixed integral. When you make this definite integral and find it, it is a constant, it is a number. And that number normalizes this density to integrate to 1. So when we compare how the kernel for the likelihood looks like and how the kernel for the prior looks like, you see that they are similar. The difference is only in these exponents. So when you find the product of the likelihood and prior, P gets exponent x plus alpha minus 1 from these two, and 1 minus P gets exponent n minus x plus beta minus 1 from these two. And you conclude that this must be a beta distribution because it has this kernel P to the something times 1 minus P to the something else. If you look closely at the exponents, you conclude that this is beta distribution with parameter x plus alpha, and the other parameter, second parameter, is n minus x plus beta. So let's take a look. Before the experiment, you believed that prior on pi is beta, that P is distributed as beta with parameters alpha and beta. After the experiment, after you observe this x, which is binomial, the posterior on the distribution on the parameter gets updated. Alpha gets updated by adding x to it, and beta gets updated by adding n minus x to it. So since the mean of beta distribution is simply first parameter divided by the sum of the parameters. We can find the mean of the posterior. The mean of the posterior is x plus alpha divided by the sum of these parameters. X and x cancel, and you get x plus alpha over n plus alpha plus beta. So what happens in the process of the updating prior to the posterior in this case? The mean, in this case, a priori mean, which was alpha over alpha plus beta, gets updated to x plus alpha over n plus alpha plus beta. Now, if you look at this x plus alpha over n plus alpha plus beta, you can represent this as weighted average. There are two weights, n over n plus alpha plus beta, that weighs the estimator for the proportion, for the probability from the data only. And that's the relative frequency. And there is another weight, which is alpha plus beta over n plus alpha plus beta, that weighs the prior mean. So as in the normal case, when we had the posterior mean to be weighted average between the prior mean mu and observed value x, here, in this case, the posterior mean for this binomial beta combination is the weighted average between the maximum likelihood estimator for the proportion only from the data, which is relative frequency, and the prior mean, which is alpha over alpha plus beta. Now, I will leave as an exercise for you to show that if you have Poisson likelihood given by this expression, and if your prior is gamma, in which case this beta is a rate parameter, then the combination Poisson gamma is conjugate. And the posterior remains in the gamma family, and you see how these parameters of the gamma are updated. So check that as an exercise. Now, we saw the example in which we have single observation which was normal. The prior was, on the parameter was normal, and the posterior remained in the normal family, so it was conjugate problem. But what if we have x1 up to xn? If we have n observations, and each of those is normal with parameter theta sigma square? Well, because of sufficiency principle, it is sufficient to only put this data through x bar, to incorporate data via x bar. Instead of considering every single x, we take distribution of x bar, and for this normal distribution of x bar simply is retaining the same location, theta, but the variance is divided by n. That is property of the normal distribution. This is the property of any IID distribution with the same variance. If you take the distribution of x bar, the variability gets divided by n. And now the problem is conjugate. Instead of all these x's, you look at the x bar. The posterior remains pretty much the same. You only replace sigma squares with sigma square over n. The same thing with multiple Poissons, because if you have x1 to xn to be Poisson with parameter lambda, then the sum of x's is Poisson with parameter n lambda. And you use this to update this parameter lambda. So that one is continuation of your exercise from last time. Just show that when you have multiple Poissons, the summation of xi's is Poisson n lambda, and therefore, if you take x, vector x, incorporate through the sum of xi's, the posterior is this. Show that. Now, it looks nice. We have the model, we have the prior, and then we get the posterior in the same family. The only thing that happens is that we update a little bit these parameters of the prior to the parameters of the posterior. The bad news is that we have only a handful of conjugate pairs. I would say not more than a dozen decent ones. You can find some exotic cases, but about 10 to 12 are usable. And therefore, you have limited modeling ability. You cannot really model everything in real life with only a handful of these pairs. So in some cases, you need to go beyond conjugacy. You need to choose the prior, which is not conjugate with the likelihood. And that makes sometimes, and maybe always, problems. Because in this case, you have to find the marginal distribution m of x by integrating the product of the likelihood and the in the prior.